In this lesson, we're going to be talking about volumes of revolution again, but this time we're going to talk about the shell method, which is a little different than doing revolutions by disc and washers. All right, let's look at a couple diagrams of what's going to be different when we use the shell method. If you look here, we're going to rotate around a vertical axis of revolution. So you're looking at something like the y-axis is going to be what we're spinning around. And then what we're going to do is we're going to draw our rectangles so that they're parallel to the axis of revolution. Remember back when we did like a disc problem, if our graph looked, let's say like that, and we were looking at this area, when I revolved around, let's say the x-axis, I always drew my rectangles to be perpendicular to the axis of revolution. Now I'm going to draw my rectangles to be parallel to the axis of revolution. All right, so what's going to happen is if you look at this example, if I spin it around the y-axis, my picture is going to end up looking something like this, where here's my cylindrical shell. Now the shell is going to sort of resemble something like this. You've got a cylinder. Oh, that's a terrible picture. Let's try that again. So you've got a cylinder with a little bit of thickness, and it's centered around the axis of revolution. We're revolving around the y-axis. All right, here's an example of where we're going to be going around like a x-axis. Notice that our rectangle is drawn parallel to the axis of revolution, and it's going to rotate around like that. So if you look, this is what your shell is going to look like this time. So we're going to end up with our cylinder kind of on its side, and it's going to be centered around the x-axis. Now we do need to take just a minute and talk about what's our formula going to be for when we use the shell method. So let's talk about what our shells look like. Remember, these are going to be cylinders with thickness to them. So we're going to talk about what would happen if I were to take that cylinder and, let's say, cut right along that line and then fold that out. Well, what would happen is you'd end up with a rectangular prism with just a little bit of thickness. So your cylinder, when it unfolds, is going to kind of look like a rectangular prism with thickness to it. All right, so then when I find the volume of this, I'm going to do it like I would any rectangular prism. I'm going to do length times width times height. Well, the width is this part here, and that's actually going to be my thickness here. Okay, so that's going to be the width. It's the thickness of your cylinder. The length is actually this distance. All right. Actually, I drew that wrong. That would be the height, the same as your height of your cylinder. So that's your height. And then the length is actually this distance. Okay, that's your height. Let's change colors here. And then this would actually be your length, because that would be the distance along here. But that's the circumference of a circle, so that would be a 2 pi r. So that when I get my total volume here, I'm going to have 2 pi r length times, I'm going to go ahead and put height next, which would be the height of my cylinder, times my width, which is my thickness, my dx or my dy. So then to find the volume, I'm going to do the integral from a to b, 2 pi, radius, height, and then thickness, dx, dy. Now, the one thing that's a little different with the shell method is the radius, because here's what's going to happen. Remember, this shell has a little bit of thickness to it, so I have to kind of decide, what am I going to use for the radius? So if I come out here, what am I going to use for that radius, or up here, if I use that for a radius? Because you actually have a couple radii there. Remember, you've got a circle inside of a circle. So what we do is we just say, well, the radius is changing, but it's either some x or some y. So in this case, if it's a dx problem, then your radius is going to be x, and if it's a dy problem, your radius is going to be y. Right? So then you'll actually fill in for your radius there either an x or a y. All right, so let's take a minute and look at an example. All right, here we have a square root graph and y equals x, and we're looking at taking this little area enclosed here, and we're going to spin it around the y-axis. All right, because we're going to do this by shells. Now, understand, this can be done by washers, but I do want to show you how to do it with shells because there are some problems. They're actually easier to do with shells than with disc and washers. So here's what's going to happen. We're going to take our rectangle. We're going to draw it parallel to the axis of revolution. When that spins around, it's going to make my cylinder like that. So then my volume is going to be, and I'm going to put my 2 pi in the front, 2 pi integral radius height, and because we're going to be parallel to the y-axis, then my thickness is actually a dx. Unlike with disc and washers, where if you go around the x-axis, it's dx, this time if you go around the y-axis, it's dx. And then my radius will be just out there some x value. And then my height is going to be a top minus bottom. Let's move this over a little bit. Give ourselves some room. And so our top would be square root of x minus bottom, which is x. And we said this was a dx problem. And now the last thing we need is our limits of integration. And these two graphs do meet at 1, 1, and 0, 0. So our limits of integration would be from 0 to 1. All right, now let's look at an example of where you would definitely find it easier to do the shell method than to do the disc or washer method. So here we've taken the area bounded by y equals 2x, y equals x plus 3, and the y-axis. So we're looking at this little triangular region, and we're going to spin it around the y-axis. So when I spin it, it's going to come over in here, and I'm just going to do a rough estimate. And here's going to be the problem. If I do this using disc and washers, I'm actually going to have to do both. Because from 0 up to 3, everything is connected to the axis of revolution, so I'd actually have a disc. But then from 3 up to the point where they intersect, which is going to be at 3, 6. Okay. So from 3 to 6, I'm going to have to do washers. So I could set it up as two different integrals, and it would be a dy problem if I did that. But it's a little easier to set it up as a shell method problem. So here's what's going to happen again. Let's kind of draw in what our cylinders are going to look like. So they're going to come in parallel to the axis of revolution. So pretend this was all symmetric. All right. Let's grab something that looks something like that. So we're parallel to the axis of revolution. So this is going to make it a dx problem. So we're going to have 2 pi integral. And then it's radius, height. We already said it was a dx problem. So then my radius, again, would just be out here some x number. And my height is going to be top minus bottom. Well, the top is the line x plus 3 minus the bottom, which is the line 2x. And then my limits of integration, since a dx problem, would be from 0 out to, we said these were going to meet at 3, 6, so it'll be 0 to 3. Okay. Now, if you wanted to do it as a disc and washer problem, here's the way you could do it that way. So I'll go ahead and show you. If I did it as a disc and washer problem, again, it has to be both. Then the bottom part would be pi integral. This is the disc part. It's a dy. Right, and so I'm going to have to do my y numbers, which would be 0 to 3, and then my radius squared. And my radius would be right minus left. Well, that would be the line here, which is y equals 2x, but I'll have to solve that for x equals and get y over 2, minus, and then the left would actually be the axis, so it'd be 0, plus, then I have to add on another integral, which will go from 3 to 6, We'll throw a dy out here on the end. And this is going to be our washer problem. And now the washer is going to be big radius squared minus little radius squared. Okay. Big radius is going to go from axis of revolution all the way out to the farthest curve away. So if I do right minus left, I'm going to have that line y equals 2x, which would be y over 2 minus the axis. And then if I do the little radius, it's going to go from axis of revolution to the inside curve, which would be right minus left, x plus 3, y equals x plus 3. To solve that for x equals, we get y minus 3 minus, that would be right, would be the line, and left would be my axis, which would be 0. So it would take both of these integrals to do the same thing as that one integral. All right, let's do one more example, and this time we're going to have one that's actually a dx problem. So what we're going to do is take the graph of x equals y squared minus y cubed and the y-axis, so we're talking about this little bump right in here, and we're going to spin that around the y-axis. That's a little hard to tell, so I'm going to enlarge that over here for us. That's 1, -1. So that's taking that, and we're going to spin it around the x-axis. I think I said y, but around the x-axis, and we're going to get that. So this time what's going to happen is our rectangles are going to be drawn parallel to our axis of revolution. And then we're going to spin around there. So our shells are going to come in like that. And this time they'll be dy problems because we're going to be parallel to the x-axis, so we're perpendicular to the y-axis. So then we would have 2 pi integral radius height dy. Now, because we're doing it as a dy problem, my limits of integration are 0 to 1. And then my height will be y this time. And then my radius, sorry, would be y. And my height will be right minus left, but the right is the curve, y squared minus y cubed, minus left, which is 0. And that would be my shell method problem.